Deep reinforcement learning contains a frustrating paradox. The mathematics behind these algorithms are elegant, but in practice, they are incredibly brittle. Run the exact same theoretical algorithm with 3 different random seeds, and you will often get 3 entirely different outcomes. One succeeds smoothly, one behaves erratically, and one catastrophically fails. The actual performance of an agent rarely comes down to the underlying mathematical equations. Instead, success is dictated by low-level code optimizations. Unnoticed implementation details, how a reward is scaled, how weights are initialized, or how aggressively gradients are clipped, often exert a more substantial impact on the agent than the core algorithm itself. This sensitivity created a reproducibility crisis in the research community. For years, engineers published papers claiming breakthrough results, when in reality, they were simply comparing their novel algorithms against reference code that was buggy and poorly tuned. The community was benchmarking against weak baselines. Solving this reproducibility crisis requires abandoning the search for better math and treating the issue as a strict systems engineering problem. The solution lies in standardizing the code architecture. Stable-Baselines3, or SB3, is the industry's definitive engineering response. Written natively in PyTorch, it is an open-source library that provides highly reliable, state-of-the-art implementations of deep reinforcement learning algorithms. Before an algorithm can be trusted in an autonomous vehicle or a robotics lab, it must prove its stability on standardized benchmark tasks, like the classic arcade learning environment. SB3 provides the vetted benchmark required to prove an algorithm actually works. To achieve this reliability, SB3 makes a deliberate architectural trade-off. It rejects the extreme single-file hackability found in research-focused frameworks like CleanRL. Instead, it enforces a rigid push-button interface modeled directly after scikit-learn. This rigid application programming interface forces chaotic models into a predictable structure. By strictly compartmentalizing the data collection phase from the mathematical optimization phase, the library ensures that complex tensor operations execute consistently across entirely different algorithms. SB3 does not introduce new reinforcement learning theory. It is a piece of critical infrastructure that standardizes execution, forcing a layer of intellectual honesty onto machine learning research. This diagram illustrates the core of SB3, the base algorithm orchestrator. When you invoke the learn method, the internal state machine dictates a continuous cycle, split into 2 distinct halves: collect rollouts, where the agent gathers data, and train, where the network optimizes its weights. Running a single simulation environment sequentially creates a massive CPU bottleneck. The network optimization must wait while the agent physically steps through the environment 1 frame at a time, crippling data throughput. To bypass this, SB3 utilizes vectorized environments. By wrapping the environment in a sub-proc backend, the framework leverages Python's multiprocessing library to bypass the global interpreter lock. It splits the workload across multiple CPU cores, flooding the collection phase with concurrent data. Parallel environment execution decorrelates the batches of experience feeding the neural network, mathematically stabilizing the training process. While massive cloud orchestrators like Ray RL-lib distribute training across hundreds of network nodes, SB3 targets highly optimized vertical scaling on a single machine. It trades extreme distributed complexity for immediate out-of-the-box deployment speed. Moving that collected data into PyTorch introduces another severe risk. PyTorch uses eager execution and dynamic computation graphs. Constantly transferring environment states from the CPU to the GPU during the rollout phase incurs a crippling latency cost. If the system attempts to dynamically resize its memory arrays to accommodate incoming rollout data on the fly, the constant memory reallocation will stagger the data flow and pause the network's forward pass. SB3 employs a strict engineering countermeasure.
Before any training begins, the framework pre-allocates the entire replay buffer as massive contiguous numpy arrays. Incoming data streams slot instantly into predetermined coordinates. Later, during the training phase, the system extracts many batches from these fixed arrays. It converts them to PyTorch tensors and pushes them to the GPU in highly optimized unified transfers. These low-level memory optimizations protect the neural network from I/O bottlenecks, ensuring high throughput between the environment and the optimizer. In simulation, a true episode termination is a physical failure, like a bipedal robot tripping over a hurdle and crashing to the floor. Mathematically, the future expected value of this state drops to absolute zero. This is distinctly different from a truncation, which is an artificial cutoff imposed by a maximum time limit. In a truncation, the robot hasn't failed, the clock simply ran out, and the agent could have continued earning rewards.
Conflating these two concepts causes a catastrophic mathematical error, known as an erroneous Bellman update. If a time-limit truncation is mistakenly treated as a physical failure, the system permanently corrupts the agent's value estimation of perfectly safe, stable states. To prevent this, the SB3 execution loop explicitly parses a hidden dictionary, called infos, emitted by the environment. It interrogates the data to distinguish a true termination from a truncation before any network updates are applied. The true differentiator between academic theory and reliable production code is the invisible handling of these silent, non-crashing mathematical edge cases. Traditional continuous exploration methods inject Gaussian noise directly into the final action output. In software, this is fine. On physical hardware, this creates high-frequency, erratic commands that cause mechanical joints to vibrate aggressively, risking severe damage. To bridge the gap between simulated physics and real-world hardware, SB3 natively integrates Generalized State-Dependent Exploration, or gSDE. Instead of corrupting the final action, gSDE samples a noise matrix and applies it directly to the internal weights of the policy network. The result is a temporally correlated, smooth exploration trajectory that a physical robot can safely and effectively execute. Hardware safety cannot be an afterthought. By embedding smooth exploration directly at the framework level, SB3 makes physical robotic deployment viable without destroying expensive equipment. This map shows the core versus sandbox philosophy. The SB3 core is fiercely protected, guaranteeing absolute stability. Orbiting it is the SB3 Contrib repository, a vital incubator where experimental algorithms, like maskable PPO, are rigorously vetted without threatening the primary architecture. Further out is the SBX project, or Stable-Baselines JAX. It acts as a strategic hedge to bypass PyTorch's execution latency, utilizing just-in-time compilation to accelerate training throughput. The ecosystem's power is defined by what it intentionally refuses to accommodate. It lacks primitives for multi-agent reinforcement learning, internal model-based planning, or distributed multi-node cloud clusters. Understanding an infrastructure tool requires knowing exactly where its capabilities stop. SB3 prioritizes a flawless single-agent execution model over complex, sprawling features. Historically, applying reinforcement learning meant spending weeks troubleshooting deep PyTorch gradient explosions or misaligned buffer allocations just to establish a baseline. Today, the primary engineering bottleneck is no longer untangling nested PyTorch loss functions or fighting silent NAND propagations. The code-level optimization has been solved. The practitioner's cognitive and temporal bandwidth is entirely freed to focus on domain-specific problems, kinematic constraints, accurate simulation physics, and dense reward shaping. By turning complex reinforcement learning into a reliable utility, Stable-Baselines3 shifted the engineer's role from writing algorithms to designing the constraints and rewards of the domain problem.